This lecture is part of a series of lectures on algebraic topology and will be a sort of introductory lecture where I will just try and give a quick overview of what algebraic topology is about. So the main goal is to understand all topological spaces. And not only do we want to understand all topological spaces, but we also want to understand all continuous maps from a topological space X to a topological space Y. Well, obviously this is far too ambitious and there's absolutely no way we can understand all of these. So what we do is we try and focus on nice topological spaces, whatever nice means, and we want to try and understand continuous maps between nice spaces. So let's just look at an example. Let's take maps from a circle S1 to a circle. So we're just trying to investigate all continuous maps from one circle to another circle. And if you try and imagine a map from a circle to a circle, there are several obvious maps. First of all, you could just have the identity map where as you go round this one once, you go round this one once. Or as you go round this one once, you could go round this one twice, or you could go round once anti-clockwise. And you could go round at different speeds, but somehow any two maps where you go round the same number of times, you can deform one into the other. So roughly speaking, if you try and draw a graph of a map from a circle to another circle, you might think of the circle as being the real line modulo the integers. So to draw a map from a circle to a circle, what you have is a sort of some sort of graph from 0, 1 to the reals, except the difference between the two endpoints of the graph should be an integer. And if you've got two graphs and the distance between them is the same integer, then you can kind of deform one to the other just by sliding this gradually from one graph to the other. So the idea is that although the space of all continuous maps from a circle to a circle is infinite dimensional, somehow you can almost classify them by an integer. So we have an integer invariant, which can be called the winding number, which is the number of times you go round the image circle as you go round this one once. And the winding number almost classifies continuous maps. It classifies continuous maps up to deformation, that if two maps have the same winding number, you can kind of deform one into the other. And this deformation is called homotopy. So homotopy is a very fundamental property of algebraic topology. We say two maps are homotopic if you can deform one map into the other map. And I'll define it a bit more precisely later. You can also think of it like this. We can think of all the continuous maps from X to Y as being a topological space, and then two maps from X to Y are homotopic if they're in the same component of continuous maps from X to Y. Actually, to be honest, that doesn't work terribly well because it turns out there are some tricky technical complications in defining the space of all continuous maps from X to Y in general, but we won't worry about that too much at the moment. Let's have another example. Suppose you're looking at maps from S1 to a torus. So a torus might look something like this. So it's actually isomorphic to S1 times S1. And you see there are several different ways you can map S1 to a torus. For instance, you could map it so that it kind of goes round the torus there, or it could go round the torus like that, or it could go round the torus in a completely different way. It could go round like that. And you can see these two red images of S1 are kind of homotopic because you can slide one into the other. And it's very plausible that the red one is not homotopic to the blue one. There seems to be no obvious way to slide this red map into the blue map. And later we will see that they really are different. So what we do is, if we've got two topological spaces x and y, you sometimes write the bracket of x and y as being homotopy classes of maps. Maps will almost always mean continuous maps from x to y, where homotopy classes means two maps are considered the same if you can deform one into the other. For example, the homotopy classes of maps from S1 to itself just turns out to be, can be identified with the integers z, because you can just take the winding number. And one of the real big surprises of algebraic topology is the set of homotopy classes from x to y often turns out to be a group, and very often this turns out to be an abelian group. And this is really quite amazing, because if you take x and y to be discrete spaces, so they're just sets, well, if you've got two sets x and y, there's absolutely no reason why the space of all continuous maps, in other words, all functions from x to y, should be a group. So it's really quite unexpected that when you look at homotopy classes in algebraic topology, this very often, not always, but often turns out to be a group in a natural way. So here we have the basic problem of algebraic topology is, if we're given nice spaces x and y, how do we calculate this set, or if we're lucky, this group? And let's have a look at a few examples of it. So the first example we're going to look at is called the fundamental group. It's also called the Poincaré group. And it's also called the first homotopy group. So the fundamental group of a space X, the idea is as follows. What we do is we look at all paths in X. And so if we've got a space X like this, we can look at a path, goes, say, from one point of X to a second point of X, and we can look at a second path in X. And we see that we can sort of compose these paths to get a third path. So we've got a sort of product on paths. And this product is sort of associative, because if we've got a third path there, it doesn't matter whether we first go from there to there and then go to there, or first go from this point to this point and then go all the way to that point. We get the same path. So we seem to have some sort of associative operation on paths. Well, there's a bit of a problem here, because you notice that the composition is not always defined. We need the endpoint of one path to be the beginning of the second path in order to compose two paths. So in order to deal with this, what we do is we pick a base point, x0 in X, and now we're going to insist that all our paths start and end at X. And now if we've got a path starting at X and ending in X, and we've got another path starting in X and ending in X, we can compose these and get a path that again starts and ends at X and also goes to X somewhere in the middle, but that doesn't really matter. So we're going to define the fundamental group of X to be the homotopy classes of paths. Well, what's a path? Well, it's going to be a map from the interval to X, which takes the endpoints 0 and 1 to the point x0. And when we deform these paths, when we're deforming them, we must always make sure the endpoints of all the deformations stay at this base point x0. Incidentally, this is another basic feature of algebraic topology. Very often, it turns out, instead of working with a space X, it's much more convenient to be able to work with a pair of spaces. So here the pair of spaces is a single point x0 together with a point x. So the second space is rather trivial in this case. For example, what's pi1 of a circle? Well, if our space X is a circle, well, we should really choose a base point, S0. And then we want all homotopy classes of maps from the interval that start and end at S0. And it's very plausible that these paths are all determined up to homotopy by the winding number. In other words, how many times you go round the circle. And this is indeed true. So the fundamental group of the circle turns out to be Z. So a slightly more complicated example, what happens if we look at the fundamental group of a space? Say we take two circles joined at a point. So we're asking how many, what do the paths look like that start at this point and wander around here and end up back at this point? Well, there are two obvious, very natural paths. We can take the path A, which goes round this one, or we can take a path B, which goes round this bit here. And then we can compose these. So we could go along the path A, and then we could go along the path B, and then we could go back along the path A in the other direction, and maybe go twice along the path B, and so on. So we can describe lots of paths that are just words in A and B. And you notice this is looking awfully like the free group on two elements A and B, where the free group just means sort of all ways of multiplying elements A and B and their inverses with no relations at all. And in fact, the fundamental group of two circles joined at a point does indeed turn out to be the free group on two generators. We've talked about the first homotopy group. So the first homotopy group is something to do with maps of the unit interval to a space that map the endpoints of the interval to a single point. Well, you can also think of the fundamental group of x with respect to a base point x0 as being maps from S1 with a base point S0 to x with a base point x0. And you may ask, what's this big deal about taking a one-dimensional sphere? Well, we can also take an n-dimensional sphere, and we can define the nth homotopy group of x with x0 to be homotopy classes of maps from an n-dimensional sphere with a base point S0 to x with its base point x0. And these are called higher homotopy groups. It's not immediately obvious that they are in fact groups, but we'll maybe showing this later. And these turn out to be incredibly difficult to calculate. Even the problem of calculating the nth homotopy group of an m-dimensional sphere is, well, this has been a sort of central problem in algebraic topology for almost a century. So, for example, here I have Wikipedia's page of some calculations of these homotopy groups of spheres. So you see the left-hand column gives some spheres, and along the top we have the homotopy group, and the bottom left coloured part of the table doesn't look too bad, but if you look at the top right white part of the table, it seems to be very complicated. There are all sorts of random looking abelian groups, and it's not so clear what the pattern is. In fact, people have found plenty of patterns in there, but we still don't really understand these groups in general. That people have calculated them a long way for m and n up to a few hundred without really being able to see what the general pattern is. So let me give just one example of an element of non-trivial element of a homotopy group of spheres. Suppose we look at pi3 of S2. So what we're trying to do is to find an interesting map from a three-dimensional sphere to a two-dimensional sphere. I'm going to ignore base points for a bit, since they don't really matter all that much. And one good example of this is called the hop fibration. And this is as follows. What we do is we think of S3 as being the set of pairs of complex numbers Z0, Z1 in C2, such that Z0 squared plus C1 squared, or rather the squares of the absolute value, is equal to 1. And if you think about the real and imaginary parts of it, this just says that these points form a three-dimensional sphere. So how do I map this to a two-dimensional sphere? Well, a two-dimensional sphere can be considered as the points of projective space. These are pairs of points z0, z1, not equal to 0, 0, where we think of this as being equivalent to the point lambda z0, lambda z1, with lambda a complex number. And you can identify this with the complex line union a point at infinity, but by just taking the quotient z1 divided by z0, which will usually be a complex number but might be infinity. So we've got a nice map from S3 to S2, where S2 is thought of as the complex projective line. You can also see the fibres of this map are all copies of S1. This might make you think that maybe the three-dimensional sphere is actually equal to the two-dimensional sphere S2 times S1, but it turns out that S3 is not equal to S2 times S1, as we will see later by calculating its homology groups or something like that. This is an example of something called a fibre bundle. The map from S3 to S2 looks locally as if S3 is a product of S2 times something, but globally it isn't. Anyway, this gives us a non-trivial, interesting element of the homotopy group pi3 of S2. This seems rather discouraging because the simplest possible non-spaces you can imagine are spheres, almost the simplest possible. And if we can't even calculate the group of homotopy classes and maps from a sphere to another sphere, this suggests we don't have much hope of doing more complicated examples. But one of the paradoxes of algebraic topology is that the homotopy classes and maps from X to Y are quite often easier to calculate if X and Y are more complicated spaces. So we get lots of invariants of topological spaces called generalized homology and cohomology theories by fixing X and Y. For example, if we fix X to be something interesting, we might, if we're lucky, get a homology theory which takes any space Y to the homotopy classes and maps from X to Y. And similarly, if we fix Y, we might get something called a generalized cohomology theory. So I'll now give a few examples of some homology and cohomology theories. So first of all, we have the original homology and cohomology theories. And although these can be represented as spaces of homotopy classes of maps, they were originally discovered in a slightly different way. So the nth homology group of a space X is defined informally as n-dimensional things in X modulo boundaries of n plus 1 dimensional things. Well, obviously, in order to make this precise, I need to tell you what a thing is, which I'm not going to do this lecture, but I might do later. Instead, I'll just give an example. Suppose, for example, we take a torus. Then we might have an example of a one-dimensional thing, might be a sort of circle in the torus going round like that. And we might take another one-dimensional thing. Well, the difference between these is really a boundary of a two-dimensional thing, because we can have this sort of two-dimensional green thing here, and you can see its boundary is this circle minus that circle, at least if you orient anything. So we can think of informally as these two red one-dimensional things should be considered equivalent in the homology group. On the other hand, we might take a different one-dimensional thing, which might be this blue circle going round here. And if you try and make the blue circle and the red circle the boundary of something, you won't be able to do so. So this suggests the blue circle and the red circle are actually different. In this particular case, it turns out that the first homology group of the torus turns out to be a product of two copies of Z, where one copy of Z kind of corresponds to this red circle and the second copy of Z corresponds to this blue circle. Now, if you remember the picture I did for homotopy, you notice this looks very much like the pictures of circles in a torus that I had earlier. So you could also think of the first homotopy group of a torus as being represented by maps from a circle to the torus, and it would look very suspiciously like this. In fact, it turns out the first homology group of a torus happens to be naturally isomorphic to the first homotopy group of the torus. In general, for more complicated spaces, these two groups need not be the same, but they're still quite closely related. There's always a map from the first homotopy group of a space to the first homology group of a space, and it's sometimes, but not always, an isomorphism. There are several variations of homology and cohomology groups, because you can do things like take homology groups and cohomology groups with coefficients that I'll be talking about later. Another example of generalized homology theories are so-called K-theories. So the geometric meaning of K-theories is if you've got a space X, we look at a vector bundle, we look at all vector bundles over X. So what's a vector bundle? Well, a vector bundle means we associate a vector space to each point of X. And we have to do it in a nice way that I'm not going to bother explaining in detail. For instance, one trivial example, we might take a space X, and for each point of X we associate the vector space R to the n. So we get the vector bundle. You think of this as being a map from X times R to the n to X. So the fibre of each point of X is just a copy of R to the n. A slightly less trivial example, we might take X to be a two-dimensional sphere S2 like this. And then to each point of X, we're going to associate its tangent space at that point. So that will be associating a two-dimensional vector space to each point of the sphere in a nice way, because if you vary the point, the tangent space varies nicely. So this will give us a map from the tangent space, or the tangent bundle, which is a sort of all tangent spaces put together in some sense, to the space S2. And it's very plausible that this is different from mapping S2 times R2 to S2, and in fact showing that these two vector bundles are different is one of the things we'll be doing later. The so-called K groups of a space X are something to do with taking all finite dimensional vector bundles over X and making them into a group. And there are several variations of this, because you can do real vector bundles or complex vector bundles or various other variations on this. K-theories turn out to be more powerful than homology and cohomology theories that we discussed in the previous sheet, but they're more difficult to calculate. Some other generalized homology theories that are even more powerful and even more difficult to calculate are so-called boardism or Coboardism theories. And the idea here is, if you've got a space X, what we do is we look at all maps from a manifold to X. It need not be injective. You can sort of define an equivalence relation on these. So we take maps from manifolds, space of all maps from manifolds to X, and we identify these by if a manifold is a boundary of something else, we sort of consider it to be trivial. So we take the space of all maps from manifolds to X, and the idea is we try and quotient it up by the set of all manifolds that are boundaries of manifolds. So even if x is a point, this is pretty difficult to calculate, because in order to calculate the cobordism of a point, what we've got to do is to classify all manifolds. Well, we probably want them to be compact manifolds and possibly with some structure on them. I'm being very informal at the moment, and work out which of them are boundaries. So let's try and work out what the cobordism of a point is. Well, let's look at possible manifolds. Well, the manifold might be a circle mapping to a point. Well, that's no good because it's a boundary. I mean, a circle is obviously just a boundary of a disk. So we don't get anything from there. Or we might try mapping some sort of two-dimensional manifold, say a genus 2 surface, to a point. Well, again, if we've got an oriented compact two-dimensional manifold, that's the boundary of something. You can just sort of imagine filling it in with a solid torus. And you might start to suspect that maybe every oriented compact manifold is actually the boundary of something. But when you go up to 4 dimensions, you find if you take two-dimensional projective space over the complex numbers and map that to a point, you can't represent this as the boundary of something. So here's an example of a non-trivial element of the bordism of a single point. And as you can imagine, this really gets rather complicated in higher dimensions, because you've somehow got to understand all n-dimensional complex manifolds and their boundaries to work out the bordism of a point. So bordism and cobordism are very, very powerful generalized cohomology theories, but they're very difficult to calculate. An even more complicated generalized cohomology theory is one related to homotopy groups. It's actually called stable homotopy theory. And as I said, calculating homotopy groups of spheres has been one of the central themes of algebraic topology. And why should you be interested in cobordism theories? Well, one reason is this book here by Ravenel, Complex Cobordism and Stable Homotopy Groups of Spheres. It turns out that one of the most powerful ways of calculating homotopy groups of spheres is by using one of these rather complicated, hairy cobordism theories. The calculations for this really get very complicated. Let me just give you an example of one of the calculations from one of the pages near the end of his book. So this is part of the calculation of an Adams spectral sequence, which will tell you some of the homotopy groups of spheres, and it sort of goes on for a few pages, and you can see just how incredibly complicated these calculations become. In fact, sometimes get the impression that algebraic topologists are sort of secretly competing with each other to see who can produce the most complicated calculation of something. And the only thing one algebraic topologist likes more than producing a more complicated calculation than somebody else is finding some sort of subtle error in somebody else's calculation. So I'll just finish by mentioning possible books. I'm not actually going to follow any particular book for this course. There are lots and lots of really great algebraic topology books. I'm just going to mention one of them, which is this book on algebraic topology by Hatcher. And the reason I'm mentioning this particular one is the author has very generously made the PDF file of this book free on his webpage. So I'll put a link to that in the description of this video. Next lecture, what I'll be doing is starting on discussing the fundamental group of a topological space, which isn't actually the easiest of invariant and algebraic topology, but it's the one that's most intuitive and easiest to describe.